The next test we consider is called the alternating series test. And it might be surprising, but it is in fact the case that the alternating series test is typically used when you have an alternating series. And so yes, the alternating series test applies when you have an alternating series test. So it says if we have so that's an alternating series. This oscillates between -1 and 1, -1 and 1. Now notice, in this case, when n is equal to 1, this is -1. So the first term here is negative. But it also applies if we have -1 to the n plus 1. Now, why is that different? Well, because when n is 1, this is 2, so this vanishes. And so here the first term is positive, then negative, positive, negative. Here the first term is negative, then positive, negative, then positive. Let's actually ensure that, because the other requirement is the non-alternating portion must be bigger than 0. Now, when I say bigger than 0, not only is it not negative, it is not 0. None of the terms of this series are equal to 0. So the non-alternating portion is positive, strictly positive, and it doesn't matter which way we're starting with negative, positive, or positive, negative, they both apply. So anytime you have any such alternating series, all right, then what we may say is this: if we have two conditions are met. Number one, the limit of the non-alternating portion must be 0. The limit of the non-alternating portion must be 0. And the second requirement is, so this is and, they must both be true. The non-alternating portion is decreasing. The non-alternating portion must be decreasing. Now, one way to say that is this: the n plus first term is less than the nth term. So if n is, I'll pick a number out of the blue sky. When n is 10, the 11th term is smaller than the 10th term. Or when n is 20, the 21st term is smaller than the 20th term. So as n gets larger and larger, the terms get smaller and smaller. That's what this requirement says. an is decreasing, and the non-alternating portion has limit equals 0. Interestingly, perhaps, when you're working with the alternating series test, the only thing you're looking at is the non-alternating portion. But actually, as a way to help remember this, the alternating series test, the only thing you work with is the non-alternating portion. If these two conditions are met, then the series converges. If they're not met, then we don't know whether or not it converges. Actually, it turns out if this is not equal to 0, then the terms don't go to 0, and the test for divergence would take precedent. And if it's not decreasing, there's no way that this could occur, and so there are some issues happening here. So, if this limit is equal to 1, then we don't get to conclude this convergent. Or if this limit is equal to anything other than 0, then we do not get to conclude that it converges. So there's the alternating series test. Even though if you go to further study, you might apply this in some larger setting, for our purposes, key disclaimer, for our purposes, this is primarily to get at one key result. This is a theoretical stepping stone to get to this key result. There is one particular alternating series that is of interest. It's this one. If you don't have this piece, that's the harmonic series. But you do have this piece, it's alternating. So this is the alternating harmonic series, and it has a special name. The special name for the alternating harmonic series is the alternating harmonic series. Now, we know already the harmonic series diverges. Let's see what happens here. first off, the conditions are met. It is harmonic, and the non-alternating portion is always greater than 0. Now we have to see if our two conditions are met. We need to take the limit as n goes to infinity of the non-alternating portion, and it must be decreasing. All right, we must check to see if both of those are true. Well, this is certainly true, because if this goes to infinity, our infinity arithmetic says this is 0. So condition number 1 is clearly met. Condition number 2, is this a decreasing series? Well, there are a couple ways we can know this. Let's see, here's one way to know that this is true. One way to know that this is true is we know what the graph of this thing looks like. Consider the associated function, right? We know that graph is decreasing. The other way to know that this is decreasing is we know the derivative of the alternating function is negative 1 over x squared. This is negative, this is positive, this is negative, and so f is decreasing. Another way we know this is decreasing is if I take an plus 1, is that less than an? Well, what is an plus 1? This is 1 over n plus 1. Is that less than 1 over n? Now, one property says when you invert two fractions, if a is less than b, when you form the reciprocals, this side is now greater than this side. So when you form reciprocals, you reverse the direction of the inequality. And so the only time this is true is if this is true. The only time this is true is if this is true. And the only time this is true is if 1 is bigger than 0. Since this is always true, so is this. Since this is always true, so is this. Since this is always true, so is this, and therefore it's decreasing. So any one of those arguments is sufficient. You don't need all three of them, but any one of those is an argument that says, yes, this condition is met, and therefore the two conditions for the alternating series test are met. And so what we may say is the series negative 1 to the n plus 1, 1 over n. Now, we could also have started with n, but typically we don't. Typically, the alternating series starts off with n equal 1. This is positive 1 over 1. Typically, the alternating harmonic series starts with positive. So this series converges. So the series itself converges, but if you leave off the alternating portion, it diverges. That's a key result. The harmonic series diverges. The alternating harmonic series converges. The harmonic series diverges. The alternating harmonic series converges. All right? Now, from that, in fact, I'm going to write this up over here. So I have this still, negative 1 to the n plus 1, 1 over n. This converges. I want to keep that here for my discussion that's going to follow. There is a notion called converges absolutely. Or sometimes people just say, they'll reverse it a little bit, they'll say absolute convergence. Those mean essentially the same thing. They mean the same thing for our purposes. Those are interchangeable. What does it mean for something to have absolute convergence? Okay, so if we have a series, this can be anything. It might or might not have anything constructed in there. This converges absolutely. I'll say, we sell this, if the absolute value, if you first take the absolute value, if you throw in absolute value out of the blue for any reason at all, throw in absolute value. If that converges, then we say this is absolute convergence. absolute convergence. If it does, so this if you throw in the absolute value, that's called absolute convergence. Why you throw in the absolute value and where that comes from is a question we're going to answer pretty soon. But for now, if for whatever reason you throw in the absolute value, and if this converges, then you have absolute convergence. Not only that, if this is true, if the absolute values converge, then so does, or then, I'll say it also, the original. If the absolute values converge, then the ordinary series converges. Here's the reason this is important. Very often, this is difficult. But this might be easy. But this is what we want to find. We want to find this, but it's difficult. So what can be done is check for absolute convergence. Very often, this is easier. Or very often, the absolute value arises for some other reason. But if this is easy, then don't beat your head against a wall on this thing. Take the absolute value, show that that converges, and then you get the original one for free. All right? So if the absolute values converge, that means the original one does for free. If the absolute values converge, then the original one you get for free. What if the absolute values do not converge? If the absolute values do not converge, then you went on a wild goose chase. You don't know anything about the original. If the absolute values converge, if they do, then you get this one for free. If the absolute values do not converge, then you haven't learned anything about this. All right? It might not, there's no telling. But if it does converge, then you get this one for free. All right? If this does converge, then we say this series it has absolute convergence, it converges absolutely. All right? If this fails, but then you go back and check this and see if this succeeds, then that's called conditional convergence. Conditional convergence is when the original one does work, but the absolute values fail. Conditional convergence is when the original one does work, but the absolute values fail. If the absolute value succeeds, then you get this one thrown in with a lot for free. But if this one fails, and then you go to the work of actually verifying, if this one does converge, but this one doesn't, that's called conditional convergence. Now, here's my original series. What do we know about this one? We know this converges. All right? Suppose we did not know that. Pretend we didn't know this converges. Now, we know this converges because of the alternating series test. But pretend we did not know that. And so what we're going to do is, to investigate this, we're going to say, okay, well, let's try this. Let's look at the absolute value, the absolute, see if that works. Well, what happens to this expression when you do the absolute value? Well, the absolute value of the product is the product of the absolute values. And so that's the absolute value of -1 to the n plus 1 times the absolute value of 1 over n. And we know what that is. This is no matter what, this is always going to be 1. If this is positive 1, the absolute value is 1. If this is negative 1, the absolute value is 1. This is 1, and 1 times anything, we don't need to write that down because we know this is 1. So this multiplier, this factor is always 1. And the absolute value of 1 over n, if the number is positive, right, then we don't need the absolute value. So this expression simplifies to simply 1 over n. And what do we know about that? Well, we know the harmonic series diverges. And so there we have it. The absolute values fail, but the original, it turns out, we know the original one does work. This is called conditional convergence. And the classic example, that's really the takeaway of all this. If someone asks you for an example, of a conditionally convergent series, the classic example is the alternating harmonic series. The alternating harmonic series is conditionally convergent. The alternating harmonic series converges. It is conditionally convergent. The ordinary harmonic series diverges. So those pieces of information just need to be standard pieces of information rummaging around your brain.